Good morning, everyone, and thank you for having me talk today. Briefly highlighting the importance of geologic mapping and planning sample return. Next slide, please. So this is very exciting time, and this is a relevant discussion because we have crewed sample return mission with Artemis 3. And so not only are we getting samples back, but as we all know, this is an area of the moon that we have never been to before. And so this is a truly exciting prospect, especially for the sample science community. Next slide. And a very important aspect of the sample return is that we are going to have the geologic context for our return samples. And so we don't necessarily have that for lunar meteorites, but with a crewed mission, we'll have geologic context, and that will be crucial for answering science hypotheses. And so we'll be landing and gaining in situ observations at the surface for ground truthing our remote observations. And I think Dean will be talking a little bit more about that in the next talk. But with sample return, we can then conduct microscale measurements in laboratories back on Earth. These high resolution measurements enable us to address outstanding questions in lunar science that Jake mentioned, but specifically for the sample science, we can do measurements in the lab based off of chronology or the volatile content of the samples or even the paleomagnetism. And so really the true scientific value of these measurements depends on the geologic context for where exactly these samples come from and how they were sampled. And these lunar science questions relate to not only questions that are in the Artemis 3 Science Definition Team report, but also general planetary science questions that were noted as really high priorities to study over the next decade by the Decadal Survey. Next slide. And again, I don't need to tell everyone here that geologic mapping is the foundation of that sample campaign. Kelsey talked a lot about that with the JET test, but this is truly an essential component if we aim to answer our scientific questions with these return samples. And so the maps can help us identify unit contexts or the relative stratigraphy of units, hypothetical sources of impact ejecta, and also see what units might be more representative of the region or what might stick out as something that's unique. And all of that helps us identify what we would want to sample in order to answer our science questions. But it also helps us identify what type of sample we want and where exactly we want to get it from. And so do we want to use a drill core to sample these potential overlying units? Do we want a chip from a boulder, outcrop? Do we want a surface regolith or sealed sample from a shadowed region? Really planning the sampling campaign is going to be oriented around these geologic maps in order to conduct hypothesis-driven science. Next slide, please. And I think that a really important aspect of all of this is that the crew is conducting science in real time, and they're the ones that are actively taking the samples, and they may also be conducting scientific experiments and measurements. And so they're relaying lots of observations back to the science backroom, and importantly, this pre-mission geologic mapping helps give them familiarity with the region. It gives them a sense for what the major craters are in the region or different locations of boulders, just a general familiarity that helps them know, like, once they're on the ground, like, is this what we expected or not? Where am I? And how do I go find the sampling region that we want? And I think another important thing in training the crew that is emphasized is to also familiarize them with these science goals of the sample campaign, and which really allows them to be empowered to make decisions in real time. Next slide, please. And I think this was summarized well by Gene Cernan in an interview after Apollo 17, where he highlighted that their descriptions were one of the most valuable contributions to lunar geology. And so again, it really is this geologic context that we need when interpreting the sample measurements back on Earth. And if you go through the Apollo transcripts, they're very rich with scientific information that ultimately supports the sample science. You can see them relating what they were seeing back to volcanic glasses in Hawaii, or saying that a rock looks like the dacite they saw in California and that it's more viscous. And so these are observations that they're making in real time and relaying back to help us decide what to sample. Next slide, please. And because Apollo 17 is our most recent crewed sample return, I wanted to pull a couple of examples from the transcripts that I think highlight the importance of the geologic maps to this real-time science that the crew is doing. So both of these instances here are on their way to Station 2, which was the longest distance that was traveled away from the lunar module during the Apollo program. This station was picked so that they could characterize the South Massif bedrock and determine the origin of the light mantle material in the region. And so they're driving across different units and sampling them as they go. They stopped about 3 times on their way there. And you can see they're wondering, are we in that light mantle yet? Ultimately, they were trying to get to this pre-planned science destination using their geologic map that was in the LRV as an atlas for their lunar road trip. And so you can see Jack says, like, yes, we're where we wanted to be once they're setting up Station 2, which is where this pano was taken. And so I think this is just like a really great example of how the crew is consulting the geologic maps in real time, specifically in order to actualize our sampling strategy that was pre-planned. Next slide, please. In addition to the descriptions of the regional geology, there's also smaller scale observations that the crew is making during the sampling that are equally important to addressing our science questions. So here is a boulder at that Station 2, and you can see where on the boulder samples were taken. And one of those samples is pictured to the right. The sample is numbered in a specific way, and Barbara Cohen's going to talk more about sample naming conventions tomorrow. But here I wanted to point out the scale cube in the bottom right. And so this is indicating the orientation of the sample, which is an important observation for our measurements and interpreting them. But there's also other observations being made by the crew about the color or the crystallinity, vesicularity, and whether or not there are inclusions and whether or not they want to sample them. And so there's a lot of important observations. Another example is which part of the sample was exposed on the surface versus the interior of the boulder, and whether something was buried in regolith or in shadow. These are all very important contexts for investigating processes such as space weathering when you are looking at those samples back on Earth. And so ultimately, it's the observations that are being made that are going to impact our ability to answer our science questions with these samples. Next slide, please.
Just under 2 minutes.
Great, thanks. And so looking forward to Artemis, we should really take advantage of our high resolution data. Kelsey talked a lot about all of the lessons that are being learned, and Jim was mentioning the scale of the mapping, so I won't go into this too much, but it just also helps us, better identify regions that we would be interested in sampling and crafting a really strategic sampling campaign. Like the increased amount of detail will help us be more strategic. Next slide, please. And so keeping with my theme today, I found these quotes from Apollo 17 that I think speak to some potential risks, such as steepness or the number of boulders. These are things that are being mapped and considered for potential Artemis landing sites, but they also feed back into the science as well. Boulder science in Apollo was a key method for sampling regions that we can't realistically access. And so whether they're boulders that have broken off from a high massif and rolled down, or potential ejecta blocks that sample a deeper part of the lunar interior, they're important for the sample science. And here, Jack was observing that the boulder density was greater than what was mapped, and even that observation alone has scientific value. And so given our higher resolution imagery, we can improve not only the science, but also the crew's safety during these EVAs. Next slide. So this is my last slide. And really, I just want to emphasize that, yes, we are returning new lunar samples, but the scientific interpretations of those samples and the overall success of the sample campaign hinges on the geologic maps and that geologic context that they provide both prior to the mission and during surface operations. Thank you.